All right, so I want to, before we get to a general overall review, I just want to kind of apply a review of some of the questions that I'm going to ask about applying the kinetics, kinematics. Remember, I'm not going to ask you to graph anything. I'm not going to ask you to interpret a graph. The graphs are just meant to demonstrate what we're talking about in a visual form, okay? So something like this, good morning guys. Something like this, a machine, even though it looks all angular, we can have an angular conversation, like the padding is trying to flex your knees, that's rotation. The knees are trying to rotate the machine, yeah? But this is very much, in terms of effort, this is very much linear. Because at the end of the day, planet Earth is still trying to pull down on that weight stack, whatever you put it. And the machine through pulleys is just redirecting everything to your shins. So remember, muscles can only pull, but they pull on bone, and those bones push on things, right? So the effort of our quad muscle, which we're going to learn at the end of the semester, which ones make it up, how they run, how they attach, how they cross. But the effort of the quad is going to be totally represented by the shins pushing on this pad. And that's going to go through the pulley system to pull on a cable on the weight. So my application of understanding kind of question is, if this person is holding that position for the photo, and we look at the plate and it's arbitrary, 10, 20, just whatever that plate is, whatever the resistance is, whatever the weight is, does it make sense that this person's going to have to effort the same to hold that position? Right? They got to match it. They got to tie. It can't be less or it would start coming down. It can't be more because it would knock the machine up, right? So from this position, she speeds up the knee flexion. Obviously, she's not just going to let go, right? In a realistic range of motion, the knee flexion is going to speed up because her effort is going to be a little less than the machine. She's going to let off. Her shins are going to push a little less than the padding to let planet Earth speed up the flexion by allowing planet Earth to speed up the plates coming back. If she maintains a constant slow speed of flexion, she no longer has to let planet Earth be greater. If she's going to keep the same speed of those plates coming down, she has to effort the same again. She has to tie again. She's going to actually be doing the weight. Because think about it, if she keeps doing less, it's going to keep speeding up. And if she starts pushing more, it's going to start to slow down. The only way to keep that plate going down at the same speed is if she's actually doing the weight she thinks she's doing. To me, that's a magical piece of information that is very useful. You're actually doing what you think you're doing as long as the speed stays the same. But when it comes time to slow down the flexion, that's when her effort has to be more, right? Because option number one is just to let the plates clang, but we are not clangers, as I established in 310, right? Gravity can't speed her up and slow her down in the same direction. So her only choice is when she gets to the end of her range of motion, she has to effort more than the weight in order to start slowing it down. She has to continue to effort more if she wants to speed it up, coming up. Tie, if the plates are going up at the same speed, and then the tippy top, she's going to let off. She's going to let gravity slow it down. And she's just going to repeat the cycle over and over again. So again, the point is to show you that during ranges of motion of exercises that we predominantly do, are there exceptions? Sure, the routine, we killed the mosquito by going faster than gravity, but that's super rare. Usain Bolt, the professional sprinter, only goes faster than gravity a fraction of his life. Most of our motion is slow and controlled by either fluctuating more than gravity tying gravity if we're going the same speed, or less than gravity. Sometimes we let gravity do certain things for us. Okay? So I have another visual of this application. So let's say this one right here. Copy, paste, and I say, okay, he's in this machine holding this position. The weight stack is off of the rack. So in other words, gravity is now trying to flex his knee, right, through the machine. So a question on the test might be, from this starting position, he speeds up the knee extension. Would his effort be the same as the weight stack, less than the weight stack, or more than the weight stack? Would his effort be less, the same, or more? And I'm not going to give any other choices than that. You got a 1 in 3 chance. What would you say? More, absolutely. And you can do a process of elimination. To hold that position, he's got to tie, right? It's a constant. And if he chooses to effort less, then it'll start to come down. True. So the only way to speed up the extension, thus make the weight stack go up against gravity, is to be more. More, less, the same. Those are going to be your answer choices for these types of very, what I consider common exercises. Yes, ma'am.
Could you explain how, in this example for the last one we did, kind of what it would look like with the negative acceleration, positive acceleration?
Absolutely. So I'm going to graph it.
Even if you don't graph, like, are we going to be, could we be responsible for answering that even though we're not graphing?
I'm just gonna, I'm saying the kind of questions I would totally ask right there. Yeah. Now, the kind of like, what's the acceleration? I would feel more comfortable asking that, like for the ball toss that we did in class, right? So like, I tossed a ball and it's in the air and nothing else is touching it. I feel more comfortable asking those kind of questions like that. I would not ask those kind of questions like with an actual exercise type stuff. The kind of questions that I would ask is like, would your effort be more, less, or the same? Yeah, because, and to follow up with that really, really good question, although linearly it's pretty cut and dry, once we get into the machines, because now we have to establish positive, negative spin, and that is based on our definition of what we want to call positive. So it would just literally be like, to hold that position, your muscles have to match the resistance. And if you want to speed up going against the grain, you got to be a little more. But you don't have to keep being more while you go through the range of motion. That's the important part. Once you move furniture, guys, it takes a lot to get it going, but it doesn't take as much effort to keep it going. I think that's the best analogy. And then once you get the furniture moving, it's super easy to stop. Just stop pushing. It'll stop. So it's very simple. Once you get to the end of your range of motion, you just let off. Gravity will stop. Now, when I say let off, you don't let off completely, right? But you let off as a comparison with what you were efforting. You just effort a little less at the top of the motion. Very good clarification. Okay, let's get to you guys. What do y'all want to know, or what do you want clarified for your test? No holds barred. You could ask whatever you want. Definitions. Key, the majority of tests is going to be definitions or inverse definitions. That's a fancy way. I don't even know if that's the right way to say it. But that's basically saying a rotational force is which of the following. Right? So I'm not asking you to define a moment, but I'm asking you to identify which of the following is a rotational force, which is a moment, right? So it may be something like that, where I ask the definition in the question, and I ask you to identify which of the following terms fits that definition. About 25. And I do that on purpose. First of all, with a mixed crowd, there's going to be some people that want a little more. There's going to be some people that want a little less. My thought process is you have 50 minutes. That's 2 minutes per question. And some questions might take a little bit more thought. Some questions might not. But typically when I go past 25, it's, oh God, I have 5 minutes left, and you start to get anxious. And I'd rather you put more thought into questions or have time to go back and double check answers. So that's why I specifically choose those numbers, is to give you time to make sure you're not just at the end, C.
You go for an angular example?
Sure. An angular example of both kinetic and kinematic, like force and motion. Okay. So an angular example for our class would be like, gravity is trying to do what to my shoulders? Right? Like adduction. I mean, I wouldn't do like fancy stuff, but just gravity is trying to extend my elbow, right? So the angular kinetic is gravity is applying an extension moment, an extension torque, an extension force. Because remember, torque or moment is just a rotational force. So you got to have a force, but that force is trying to spin something. It's a spinning force. So if you had some children that y'all were in class and y'all went like on a lab and the children were on the merry-go-round, not any force is going to spin the merry-go-round. Like if you push into the merry-go-round, you'd be the worst friend that you've ever had, right? You have to apply your force very specifically, perpendicular to the axis of rotation, to the force application. I'm not asking us to go into that kind of detail. I'm just asking us to understand that certain forces are trying to spin things. So linear kinetics would be gravity is trying to adduct my shoulder. It's an adduction pulling force, or it's an adduction wanting to cause force. My internal muscles, then, if I'm going to hold this position, are trying to adduction. So I'm going to have abduction torquing. I want to make sure I said torquing and not giving forces. So then what is the kinematic conversations? Well, that's the actual motion you observe. So if I'm not observing any motion, that's my kinematics. The position stayed the same, so no change in position, no change in velocity, no acceleration. And then you can have from here I slowly have adduction. Well, that is an angular kinematic term. So then I could say, well, what are the angular forces responsible for the? So we've actually done this in 310. It's just now slotting them into the right conversations, right? So those would be like angular examples. Or an angular example would be like for the door, right? Like, I need to make sure that my force has a rotational component. I can't open the door if I push way over here. Right? So it's not just about the force. It's about how a force is applied to make something spin. But very definition based. Very definition based. And we could go with that first question, which was really good. I could give you an example and say, gravity trying to adduct your shoulder would be an example of, right? So I could give you a angular kinetic example and just give you different options.
Did you look over the
Yeah. So motion of the vertical jump, straight up is linear, just ups and downs. Okay. So the movement of your vertical jump. So it would be terms like, and first of all, if you're doing a vertical jump, it's about your center of mass, right? So And I would establish that on the test in terms of asking the question. So what I mean is the weight stack would be you. This would be your weight stack. So it'd be like from here, I'm gonna speed up coming down, right? But you know what I wouldn't want to do? I wouldn't want to elevate it, right? Like if I'm doing a vertical jump, I kind of want to go down fast so that my force that I apply to the ground is going to be great, because that's ultimately what's going to make me come back up as fast as I can, right? So in other words, the strategy you don't want to have is like you would like doing squats or exercises, right? You actually kind of want gravity to let you free fall. Okay, so you're going to speed up coming down. Now you just asked about kinematic, so you're going to get further and further away from zero, right? So it's going to kind of look like this. And then once you start to push on the ground, thus the ground pushes on you because of Newton's third law, with more than your weight, you're going to immediately start to slow down while you're still going down. So this point C is actually going to be your lowest that your center of mass is going to be at the bottom, like that's your bottom. You're going to keep pushing more, change your direction, and you're going to speed up coming up. Speed up, going up. And then what happens at point D to your motion? You leave the ground. So once you leave the ground, the only thing pulling on you is planet Earth. So that's a negative acceleration. So you're going to slow down coming up. That's your tippy top. Planet Earth or gravity is going to speed you up coming down, and you're going to hit the ground again. So I would not ask, especially on this test, to talk about like angular kinematic stuff. The only time I would talk about angular kinematic would be like if we were doing like a very basic exercise like the leg extension machine, like speeding up the flexion or slowing down the extension. It's very basic. Because remember, guys, this first test is just us practicing and learning these terms, so that eventually when you apply it to your skill project, you can kind of be on the same page. But it makes sense why, like, for a vertical jump, you wouldn't want to have a nice slow and control, right? Is a vertical jump's not like an elevator taking you up or down. Like you want to go as fast as you can coming down, and you want to go as fast as you can coming up. The cool thing about as fast as you can going down, you only got what gravity can give you. You can't make yourself hit the ground faster than what gravity can unless you're pulling on something. That makes sense? Where are my football fans out there? Okay, some good football last weekend. You ever notice it's always hard when a running back or wide receiver initiates going down, you never get a clean shot on him because the person who's about to tackle him can't make them go down faster than what the other person. So it always seems like the person who initiates it gets under them because you can't swim your way up really fast.
Can you give me an example again that you gave for head? Like, can you walk through it?
Or can you give me an example of like the movement? Sure. Let's go to, so if we were going to do angular kinematic stuff, that would be like joint motion analysis, right? So like, so for this exercise, why do I always X out? I'm such a goofball. So let's say for this exercise, we were describing the motion. So from here, we're going to observe knee extension. Then the knee extension is going to change direction, then the knee flexion, then the knee extension. Or what is my position of the knees? My knees are flexed because we learned that position is referenced to anatomical. So in other words, it doesn't matter if he's flexing or extending, he's in a flexed position. So angular kinematic conversations is just where are your joints? How are they moving? Prior class. You can have angular kinematic conversations about the baseball spin rate. You can have angular kinematic conversations about the door opening and closing, but for us, it's going to be applied mostly to our movement, our human movement.
No, you ask that question again?
In English,
Works.
that's always a tough question because I don't write the exams until like I actually want to have the reviews and kind of see where everybody's at, see what they're comfortable in. But it would be a question like, if we, now this is, don't misunderstand, I'm not saying I'm going to ask this, but this is just like kind of how I put. You observe knee extension in this exercise. That would be an example of, it wouldn't be linear kinematic, right? Because I'm doing extension, which is a rotational movement. It wouldn't be linear kinetic. It wouldn't be angular kinetic because we're talking about motion of a rotating body. So it would be that. I would not ask this, but to clarify, if I say hands go up, that's not angular, right? So it's all based off of, if we're talking about like a joint position or a joint motion, that's rotational movement, and thus it's angular kinematics. Did that satisfy your question? Awesome. Yeah, I always struggle with what I can ask and what I will ask, because I haven't written it yet, but it would be something like that. Remember, guys, I'm just trying to see if you could differentiate up, downs in forces in motion and forces in motion in spin. Like slotting them, if that makes sense, right? So if I say the car is traveling 55 miles an hour east, that's a linear kinematic variable. But if I say like the wheels are spinning, or like you turn to the right, or like there's ways that we can make it angular. But if I just say the car is traveling east, the car could be in a tow truck and not be spinning its tires, but still be traveling east. So straight line force, straight line motion, spinning forces, spinning motion. Do you mind saying that one more time? The ball, sure. Growing up, when I was sick, I'd go to my mom's, and she would always watch the soap operas. When they'd have a guest actor, actress, they'd be like, the part of Landon will be played by, so the part of the ball will be played by my earbuds today, because I don't have the ball. So, ups and downs, so this is linear. The forces that the ball feels is kinetic, and the motion, position, displacement, velocity, acceleration, those are the kinematic terms. And we know that the kinetic influences or changes the kinematic, right? So they're related, but they're two separate conversations that happen to be in the same equation, Newton's second law. So if we were going to look at linear kinematics, what's the position of the earbuds? Well, I could say it's like 4 feet from the ground. Right? How is the position changing over time? It's not changing, staying 3 feet over the ground, so that means it's not displacing. If it's not displacing, then it's not moving, so the velocity would be, like there's a lot of different things we can infer based off of information. Right? It's not accelerating. Okay. From here, I give it a push. So I'm going to displace the ball. Remember, everything takes time to displace. Everything takes time to change. And I established in one of our first lectures that we do this all the time with like speed tests. Tests of speed, but we measure it in time. So the fact that the ball is going to displace tells me that it has to speed up, tells me that it has to accelerate. Right? And it also tells me that if the right side of Newton's second law is accelerating, there's got to be because of some force. Right? So there has to be a linear kinetic reason for the acceleration. They have to be linked. You can't accelerate without a reason. Again, that would be magic. So what was the force that sped the ball up? The push from my hands. What direction is that? Positive. So what's the acceleration? Positive. The force conversations are the linear kinetic conversations. Gravity pulling in the negative, my hand pushing in the positive. The kinematic conversations is, well, what happened to the ball? It sped up, slowed down, it's moving up, it's moving down, it's accelerating, it's not accelerating. There's a movement conversation. Okay? Once the ball leaves my hand, I can't influence it anymore, right? So once it leaves my hand traveling up or with positive velocity, immediately it's going to start to slow down while it goes up. Slowing down while it goes up is a negative acceleration because the only thing influencing this ball is planet Earth. We cannot say, well, but the reason it's going up is because of my hand. That's great. You're no longer messing with it. That was then, this is now. So the ball would be negatively accelerating as it slows down going up. Even at the tippy top, when it's passing through zero velocity, it is still negatively accelerating. And it's going to speed up coming down, still negatively accelerating because the only force acting on it is from gravity from planet Earth. And the only time it's going to stop negatively accelerating is what goes up must come down. So either my hand is going to positively accelerate it to stop it, or the ground is going to positively accelerate it to stop it. Yep. So when the ball's in the air and I'm not touching it, it has to be negatively accelerated. It has to have negative acceleration. And I know that can be confusing, but think about it. The way I do it is, all I ask myself is, if there's only one force acting on it, what direction is that force? So the acceleration has to be negative. You can't have negative left side of Newton's second law equal positive right side. If it's negative on the left, it's got to be negative on the right. If it's positive on the left, it's got to be positive on the right. So if it's positively accelerating, it means it has to be because of a positive force. And vice versa. And all objects on planet Earth have at least one thing yanking on it. That's the planet itself. So if there's only one thing influencing that object, it's got to be planet Earth. And the reason we're just tossing up in the air is because I want to make wind resistance negligible. You know, when you're pitching or throwing, or there's going to be times where you're moving fast enough where the wind is. We know this, and my dad reminds me all the time. Shad, if the difference between cruise control at 75 miles an hour is a lot more gas than if you cruise it at 70. Yes, sir. I know, but I want to get there. But that's the best stuff. The faster you go, the more wind is trying to get your way.
Could you give an example, like you just did where you related the angular the layered kinematic and kinetics with angular kinetics and kinetics?
Like an example, that would be a typical 310 question, like the light extensions, right? the machine's trying to flex you. That's an angular kinetic. It's a rotational force. You observe flexion. It's angular kinematics. That kind of stuff. Total routine. Total routine. I'm just giving them names now. Giving them names. And remember, we spent some time on the bench press example, right? So the bench press example, I think, is a good one because it has all of them in there. See the one we use out, right? So if we were talking about linear conversations, it would be like the hands go up and down, the bar goes up and down. And if we're talking about angular, we're like the bar is trying to do this to my shoulders, but my muscles are trying to do that to my shoulders. And so that's the differentiation. And remember in 310, we said we rotate to translate. I think it's a great example. Like our joints are rotating through our muscles in order to translate our hands, in order to translate the ball. And those two things don't have to add up outside of effort. So what I mean is that in terms of the linear, it's all about your hands and the weight. Has to be. But angular is a different story. I'll give you an example of what I mean by that. If I asked everybody to stand up and hold your arms out as long as you can, your effort is very minimal. But do this for a couple of minutes, your effort will start to get higher and higher and higher, even though technically the force needed to maintain the linearness is the same. But you're just like, oh my God, this thing feels so heavy. But it's the same linear. Right? So it's just an example of how, effort doesn't necessarily have to match up, and that's because of rotation. There's things like moment arm, there's other variables. But at the end of the day, ups and downs, that bar is going to be influenced by the push from your hands. And remember, muscles pull on bones, but bones push on things. So those hands are just answering the call to the angular kinetics of your muscles. It's almost like they are their elected representative. And that's cool. I think that's really cool for us to understand that, to me, here's a good practical example. If you sprain your wrist, if your wrist hurts, even though your muscles are fine, you probably couldn't bench what you usually do. Muscles are still fine, but the representation of the muscles has a bobo, so you won't do as much. You'll see that a lot in manual muscle tests. Obviously, this isn't on the test, but I like to give practical stuff. Sometimes when we do manual muscle tests and we're trying to establish pain scales or injury rates, we won't tell the athlete what we're doing. And so it'll be like, okay, hold your arm out. This one's fine. And we're pushing down, good, strong. And then I may press on the bobo. And based on how that distracts them from maintaining that manual muscle position. Like sometimes when I press a little bit on the bobo and their hand drops, that tells me, ooh, their body is very concerned with this. It's a really good question. So the angular stuff should be very routine-ish, but we're just sliding it into, we're just giving it names. We're just giving it names. What is the machine trying to do? Or what is gravity trying to do to your joints? Now, once again, I'm going to make sure I clarify. We're not giving ups and downs are super easy. Rotationals are more complex, and that's why I'm not holding you accountable for it, because we have to establish rotational direction. Like we have to say, this is positive, this is negative. And it gets tricky when you're talking about the human body because they're mirrors. Remember, in 310 we talked about mirrors. So positive rotation globally from my shoulder this way might be negative rotation of my shoulder that way, but yet they're the same. So I'm not going to get into angular kinetic in terms of quantifying it because it gets really complicated. But I just want you to know that when we're talking about 310 stuff, gravity's trying to do this, so my muscles are trying to do that. That's angular. And then the motions would be the kinetic. And the gravity, so in other words, I'm not going to ask you to tell me the direction or the magnitude, but just know like, ooh, gravity is no longer working linearly. Gravity is now a conduit of rotation. It's like if my arm is at my side, gravity is just trying to work linearly. It's just trying to dislocate my shoulder, right? Gravity is not trying to rotate my shoulder when I'm here, but it is when it's here, because I gave it distance. Here's another way of saying the same thing. Gravity is always working linearly, but it's not always working angularly. Maybe that's a better way of clarifying. And that should kind of make sense, right? Like gravity is always pulling everything to the center of the planet, but if I'm laying down on the floor, it's not trying to move my joints. We did, I know guys, this was several weeks ago, but I remember doing this example of, bless you, where when we were talking about moments and rotational forces, we did like the ankle cuff. Yeah, there it is. We did the ankle cuff example. And it was to show you that like in this position, gravity is totally trying to flex my knee. Right? It's a rotational force of gravity. But when I'm in this position, gravity is not trying to flex or extend my knee. Does that make sense? So if gravity is not trying to flex or extend my knee, my muscles don't need to flex or extend my knee. Right? I can be relaxed. I can hold this position forever. Gravity's still pulling, but in this position, it's really just trying to dislocate my knee. So there's always going to be the linear aspect to it, but there doesn't have to be always the angular aspect. What I know this is a you guys review, but just like some basic common sense things too, like when we talk about the difference between like what are the pros and cons between like dumbbells or cuffs or free weights versus machines? And we talked about that, like dumbbells are very, like they're more affordable, you can travel with them, but you're limited to gravity. Right? Machines take up space, they're more expensive, but they maintain a more consistent angular kinetic influence. So in other words, when I'm on the leg stitching machine, you know I hate that word, the machine is trying to flex me the entire range of motion. There is no limit to, oh, gravity stop, trying to flex me. And I'm here with up. When I'm on the machine, the padding is still pushing me in a direction of flexion. So therefore my muscles will be working through more of a range of motion. That's great. Why don't we do that all the time? They're expensive and they take up a lot of space. And so some of you guys, when you're going to be working with people, home health, athletics, or effort is going to be in an extended position here. So reposition them where their biggest effort is going to be in a flex position for a few repetitions here, like stuff like that. Don't need to do that in a machine if you don't have access to that, or a manual resistance. We used to do this in the athletic trainer. When they would start to flex and the rotational force would get less and less and less, that's when we would apply manual resistance like a machine had a manual resistance to compensate for it. I had a friend of mine, he was a phys guy and I was a biomechanist at Auburn, and I was like, he worked for Gatorade for a while, really cool dude. I was like, dude, let me try that. He was doing shoulder press. I said, let me try something. And when you're doing a shoulder press, at the top is kind of when you can rest, right? Like you can kind of get your breath at the top. Why? Because gravity is more parallel to the shoulder. Gravity isn't trying to adduct you at the top. So the moment the rotational influence gets less and less, so your effort is less. So John Eric, what we did is
when he would get to the top, I'd start to try to pull his arms apart. I supplied the adduction influence. So he couldn't rest at the top, and it was more consistent. And after like 5 reps, he's like, dude, I'm done. His muscles had never pulled at that angle. Y'all should learn this in physiology, but you can't learn everything. The semester's only 3 months, but muscle fibers are very angle dependent. Like if you only stress a muscle at a certain angle, you're going to get strong at that angle plus or minus 5 degrees either side. So if you're missing out on influencing a muscle in a significant range of motion, that muscle will not adapt like it does for the rest. You'll have muscle imbalances, or you'll get weak in certain ranges of motion, or stronger in other ranges of motion. That was a cool example of when he got to the top, there was no rest. I was giving him angular kinetics in a point where gravity would. This test is going to be very, very definition based, guys. I told you what you're going to have to apply, but very, very, I think this is a fair question. Like when we talk about equations, like if I give you an equation and I say if the left side goes up, what has to happen to the right side? Gotta go up. You can't make 20 equal 20 and then the left side goes up to 40, the right side's got to be 40. It's got to go up too. Same side are inversely proportional. So if I have 20 equals x times y, and x goes from 10 to 5, well then the other variable has to go from 2 to 4 to keep it the same. And I know that may sound arbitrary, but I think it's pretty important because in the real world, knowing how different variables affect other variables, to me it's no different than like in psychology, like knowing how your behavior might affect other people's behavior. It's the same thing with variables in these forms. Definitions. Yeah, this one's pretty important. It's not the weight, it's the moment. It's the example that, if I have 75-pound dumbbells, I can do internal and external rotation, but I'm not doing abduction or flexion. Right? It's not the linear kinetics in terms of our joints and the muscles and movement, it's the rotation. It's the moment, it's the torque, it's the rotation when it moves. That's what we go against. Layman's terms. Easy, hard, right, or harder. And it has nothing to do with the dumbbells. The dumbbells didn't change their weight, their mass. Your arms didn't change your weight, your mass. Right? But how far away those things were from your shoulder relative to gravity pulling them down, that changed a lot. Any of this stuff should be straight definition and examples. What if I ask, because too many times, guys, definitions of stuff are very scientific-y. I like to ask things in layman's terms, like how much time did it take you to speed up? It's acceleration. How much time did it take you to displace? Velocity. Like that kind of stuff. I think you should know
what the laws are. Yes, ma'am.
I have a question.
Yeah, go ahead.
About the push-up example.
Yeah, sure.
So it's really just a clarification about the forces part of the question.
Mm-hmm.
Because in the lab, we related everything back to the force we felt like versus the ground.
Mm-hmm.
So when we start to go down, we let up,
Mm-hmm.
so you're pushing less.
Yeah, less up. Yeah.
Once you're moving at a constant
Mhm.
velocity, you lose the acceleration. Are you doing, are you
You're
still doing
doing-
less or the same?
You're doing your weight.
Okay.
Yeah. So you're doing your weight. You're doing your weight. So the analogy that I give is if you were on an elevator and the elevator was coming down, similar to us going down on a push-up, right? I'm standing on the elevator and I see 200 pounds because the elevator hadn't started moving yet. As soon as the elevator starts to go down, it goes from not moving to moving. It's sped up, everything takes on, that accelerates. As soon as literally the ground is being pulled away from me. I'm gonna look down and I might see 198, I might see 197. I'm gonna see less than my weight. And that's actually what's gonna allow gravity to speed me up. Because again, if planet Earth stopped working and the elevator pulled away from me, I would just float. Okay? Now, as soon as the elevator hits a constant speed going down, you know this, you don't even feel like you're moving when you're in the elevator. Because it doesn't have to keep being less. If you look down at the scale, I see 200 pounds in there. Because that's the only way I can keep going at the same speed, is if they tie. And then when it comes time to slow down, the elevator is going to push up on me more than my weight. I look at the scale and it might say 202, 203. It's the same thing, but just applied to our hands or our feet. I have to let off. I have to let off my effort to let planet Earth speed me up, let gravity speed me up. But I don't have to keep letting up to keep going at the same speed. I just have to match the effort. Because think about it, if I kept letting off, I would just keep speeding up until I smash my face. And if you wanted to have an angular conversation, I think I said it earlier, but I'm not going to ask you, outside of what is it, I'm not going to ask you to identify like angular kinetic stuff because the rotations are different. But you have to establish positives and negative rotations, and it gets confusing with mirrored things. But we can definitely have angular kinematic conversation about the joint motions. Like horizontal abduction on the way down, or if you're going with your elbows in, extension on the way down of your shoulders, flexion of your shoulders on the way up. That's angular kinematic. And we could talk about angular kinetics from a muscle standpoint, like what muscles, the muscles at your elbows, the extension pullers, the muscles at your shoulder, the flexion pullers, or the horizontal abduction pullers. It's angular kinetics, because those muscles are influencing stimulus. The linear kinetics are what your hands or your feet or whatever is pushing on. Right? So again, the hands effort on the ground is linear because that's an up and down thing. And the muscles pulling on the individual joints are they. Make sense? Do you guys trust me? Oh God. I'm not going to say the test is easy, but it is easy if you know your definitions. And you know the difference between velocity and acceleration. And you know the difference between straight line world and rotational world. And you know that one example of the bench press, and when is my effort going to be less? And when is my effort going to be more? And when is my effort going to be the same? It could be fun. All right, guys, you got to go. We'll work on that trust thing, all right? Yeah, all good.
is the motion that we're observing,
Absolutely.
either for angular or linear.
Yeah.
That's general,
Yeah.
simple
Yeah.
definition that I can understand.
Correct, and keep in mind, you may not observe anything, and that's still
Yes.
kinematic, right? Like,
Yes.
no motion is still
And
technically
backward,
motion.
is it more or less of the same?
Well, more or less or the same is always gonna come back to forces.
Mhm.
Because it's gonna be the effort or the forces that are gonna mess with your motion.
Mhm.
So the more, so in other words, in terms of the effort or the push, or in terms of that's gonna be like, I'm gonna be, let's go back to this example. So if we're doing the bench press, I'm not gonna have like more or less of the same, not the same because you could have like the same velocity, right? But I'm not gonna have like more horizontal abduction or less horizontal abduction. How I would communicate that in terms of emotion would be, I'm speeding up horizontal abduction. I'm slowing down horizontal abduction.
And that is
That-
linear? That's kinematic.
Yes, and it would be rotational because horizontal abduction is a rotational movement.
Okay.
So if we were gonna say linear, I would say,
The up and down.
yeah. I'm speeding up the bar going down. I'm slowing down the bar going down. I'm speeding up the bar going up.
That's kinematic.
Yes.
What would be the kinetic?
No problem. The forces, so the linear kinetics would be gravity pulling down the bar. My hands pushing up on it. Because like my hands are like the representatives of my muscles, right? But at the end of the day, like I said, if I had a elbow, if I had a bruise on my hand, even though my muscles are fine, I wouldn't be applying the same amount of force. That's okay.
The kinematics part I'm very much
Yeah,
interested in
yeah,
is
yeah.
what you're observing.
Of course.
And then you say it's rotational, so that maybe look at linear
Yeah.
and say, okay, this is rotation. That I'm studying.
Yep.
But
You-
the
what-
kinetics.
The kinetics, what I try to look at is, I know it's F is equal to ma, but I always try to start with kinematics, because that stuff we can better see.
Yes.
It's a lot harder to see an invisible force right there. It's hard to kind of see what's happening. So I always say, okay, if this is what I see and what I observe, then I can say, well, it had to be because of these forces. It had to be because of net positive.
Big stuff I can think of, if it's linear kinematics, going up and down.
Yeah,
Then
absolutely.
I can say it's because
Of
of,
linear kinetics going up and down.
yes.
Absolutely.
And if it's rotational, I can say it's angular kinetics because I'm observing
Absolutely.
that
Rotational motion. Absolutely. And so even though this force is linear, because it has a moment arm,
Mhm.
it becomes rotational when you give it that moment arm. So even a rotational force has to have a linear effort. But what makes it rotational is that it's trying to rotate.
Those questions are making a lot more sense now.
Awesome, awesome.